and then they are on YouTube. So we will then just send you around the links on YouTube, yeah, because that works actually better as with the recording system from the university. Or you can just come to us and we can hand it out to you on a flash drive. Or another possibility is there are still all the movies uploaded from last year's class. So in the course material, what I'm doing in class, that is this year the same as last year. So you can actually already start right now to watch all the movies. Yeah, it's all up to you. They are all uploaded. I think these are 13 movies, something like this. Yeah. So or you can then watch them from 2018. Yeah. I mean, there is actually nothing different. 2017, I have maybe watched some other T-shirts in week 3 or week 2, but anything else, it's all the same. And now we can start. Can we make this bigger? Yes, that's now big enough. So now that is now our first picture, and you should by now, what is this? You had some similar pictures in ES303, yeah? And I would advise you not to throw away the PowerPoints from ES303. So because now in this class we are doing till the midterm semester break a little bit mineralogy and petrology, also a little bit crystallography, and after the midterm we are talking about metamorphic course onward. So what can we see here now? That is the subduction zone, and this subduction takes place beneath the continental crust. And where do you have here right now such a scenario? Where is the next place where you can find a subduction zone beneath the continental crust? Where is this now? That is in the Andes, and the Andes are in South America. Yeah? So there you have this situation. So now we have here this subduction zone, and now we have, or in this subduction zone, that is split in different segments. You have here the pyrrolite. The pyrrolite is a theoretical composition, and this theoretical pyrolytic composition was introduced by Ringwood in 1967, that is right now 50 years ago. So, and this is just a theoretical composition, and that is because you cannot go there and sample the rocks there, yeah? Because it is not that you can reach this area with the driller. Yeah? So, I mean, the deepest drill hole what they have created, that is now, I think it's somewhere in Germany, it's about 15 Ks, and with 15 Ks you are not coming that far. I mean, here we have already the scale 50 kilometers, yeah. There you are coming then not that far. So now here in green we have the oceanic crust, and the oceanic crust is made up of what? Yeah, that was a question. I have always question, and usually I can then always answer the question by myself. So now the oceanic crust is made up of what? There is basalt, and what is then the plutonic equivalent to a basalt? That is a gabbro. Yep. And you just check where we have the gabbro and where we have a basalt. 129, yeah. So beneath these basalts and these gabbros, I mean the basalt is chemically has the same composition like a gabbro, but it's more fine-grained, and that is because the melt which forms the basalt cooled down much faster compared to the melt which formed the gabbro. So that means on the top of the oceanic crust you have then a basalt, and beneath there you have a gabbro, yeah? So we will also see some basalts and gabbros during the field trip, because I mean here all the islands that is basaltic, yeah? You have gabbros, you have basalts, you have also tonalites, yeah, and such things. And you have a lot of very nice features like pillow lavas and so on. Say on the top here, on the top of this oceanic crust, you have sediments, yeah? So in these sediments, you have the aluminium-rich sediments that is just caused by the weathering here of the continental crust, and then the sediments or the weathered material becomes transported on the top of the oceanic crust. So, or you have some biogene sediments that is just, you have them also here around on the Fiji Islands, that is just of sedimentation of organic material on the ocean floor. So now we have this subduction zone, and you have just given them the gabbros and so on. So now we have in here this subduction zone. So now our sediments at the top and our gabbros and basalts, and beneath the basalts you have then the peridotite, yeah? And we have here also some peridotite. For example, here that is a peridotite that is actually a spinel lersolite from Poro Island. I mean, these guys you can then see on Poro Island. And here we have another peridotite from the Dreier Weiser in Germany. Yeah? So, these are underlying or beneath the oceanic crust here. There you have the peridotites. So in these peridotites can be subdivided in dunites, in harzburgites, and in lersolites. So and these lersolites can then again subdivided in plagioclase lersolites, in garnet lersolites, and in spinel lersolites. And those from Coral Island, these are spinel lersolites. So and now we are sending here the whole baggage down. So and what happens there? What happens there? So I mean you are increasing the pressure and the temperature while you are sending down the whole baggage, yeah? So and then I mean all these hydrous minerals they will dehydrate, yeah? And that forms the melt, yeah? And this melt is then rising up. So, but before you are making melt, what happens there? There you are making the metamorphic rocks. Yeah? So metamorphic rocks are generally a result of collision or of conduct metamorphism, which we will also discuss later. So and now you are forming here at the beginning, for example, a green schist, and I gave you just a green schist around from Vitilemo, yeah? So, but in Vitilemo you have not a subduction, in Vitilemo you have just a collision of single fragments. So, and after the green schist, what do you think what we are forming then? Then we are forming here maybe an amphibolite, or we are forming a blue schist. Yeah, if we can have them. Yes. So and the green schist is green because of the green color, yeah? But it's only the green schist which was formed by a former oceanic crust. Because the metaphyllite, for example, that means the metamorphosed sediment, is then also a green schist, but it is not green at all, because there is no chloride inside. So, but we will discuss this also later. So, and after the green schist, you can then form an amphibolite, which contains the amphiboles, or you can form a blue schist, and this blue schist is blue because of the Glaucophan. And Glaucophan is a sodium-bearing amphibole, and that makes the blue schist blue. So, and afterwards, you are forming then in such a scenario, for example, eclogites. And we have also a number of eclogites there. Yep, the 10 will just give them around. So now here we are forming the melt, yeah, and that is by dehydration, yeah. So and if you are forming melt, then you need that, I mean it's a product of dehydration. So and therefore if you dehydrate something, then you have to hydrate something before, yeah. So and therefore you need volatiles. And I mean, volatiles are very, very important to understand how this planet was formed and how life is possible, yeah? And that is because of water. That makes the whole thing so interesting, and therefore we can run plate tectonic, we have the magmatism, we have volcanism, yeah, metamorphism, and all the things around it. So then we are creating here this melt. So in former times, people thought always that this melt, which rises up, is just formed by the melting of the subducting slab. So, but recently, just since a few years ago, we know that this is wrong. So, because that you have the dehydration of the subducting slab, so and then you are hydrating this material here, and that is the so-called mantle wedge. And then the parts of the mantle wedge are melting up. And if you are producing melt, then you have the decrease in density compared to the surrounding material, and then the whole thing goes up. Yeah? So that is then because of a density contrast. So, and then you are forming here different types of magmas. Here, for example, you are forming an andesite. Here you are forming a basalt, yeah? So, in such an andesite or an andesite is actually a very common rock on all the Fijian islands, yeah? So, and then above here in this scenario, we have the normal continental crust, and the continental crust is chemically totally different from the oceanic crust, yeah? So, because in the continental crust you find the rocks like, here's the 10 has already the andesites, these are the andesites from Fiji, yeah, is it, yeah? And have you find the metamorphic rocks as well? Or did you found?
There's some people substitute.
Ah, you are still, yeah, it's fine. So, and then you have the continental crust here. The continental crust you should know this by now from ES106, has a much lower density compared to the oceanic crust, and the continental crust has then a density of about 2.85, whereas the oceanic crust has a density of about 3.3. Therefore, you can initiate subduction. So, then we need some granites. Yes, and all these metamorphic books. Yes, granite. Yeah, that's all granite, that's fine. So then we have some very nice granite. That is also a granite. So here you have just a bunch of granites, yeah. So, and they are looking also different. And the granites are just very coarse-grained rocks, yeah. So because they cool down slowly. So here in the middle we have then the rise up from basaltic magma, and that is here at the oceanic ridge, middle ocean ridge. So when you are removing the rising up melt, therefore you can start with the movement of plates, the other plate going here to the left and the other one going here to the right, if we would have input from the computer. Yes, here we go. So, and there, that is actually the machine or the force which causes the movement from this side to that, and this here to the right. So, and then here we have a melt, a rising up melt, and this melt is then of basaltic composition. And you are forming a residual stuff inside, and this residual melt, these are then all these peridotite, yeah? Therefore, you have here at the top of the oceanic crust the basalts, the gabbros, then you have this sheeted dye complex. We will show you a sheeted dye complex also during the feed trip. And with these you have all these peridotites like as you can find on Coral Island. Yeah? So I think I have nothing for total. No, then we can go to the next slide. Yes. So and you saw just now or right now the granites, yeah? So if you are looking at such a granite, then you can, what can you observe? Yes, you have different minerals and different crystals inside, yeah? So in all these different minerals and all these different crystals, they have a different color and they have a different shape. So in this is run or controlled by the internal symmetry, yeah? So that is the external form, and it depends always if this mineral can grow. Let us say if it has space to grow, then you can see the crystallographic symmetry very, very nice and very, very well. So, find them. So then here we have, for example, a box with a lot of typical crystal models. Yeah? Everything here, for example, that is a cube. Yeah? So in such cubes can be seen very, very nicely also in nature. Yeah? So here you have the cube, and here you have a pyrite. That is grown naturally, and that is just made by the timberman. Yeah? So, but these are the perfect crystallographic symmetries. So, but in nature they are not always so pure like this, because this one, for example, is also a pyrite. Yeah? So there you can see the cubes only on a few surfaces, because this pyrite did not have enough space to crystallize. Yeah? So but this one had enough space. So that is how, for example, a cubic mineral. So another mineral which is also cubic is where you can just leave it around. Another mineral, and the wooden piece as well. Another mineral which is also cubic is, for example, the mineral diamond. Here we have only a small one because diamonds are very expensive. So if you are looking at this mineral, that is now not a cube, that is an hexagonal mineral. So here we have the hexagonal crystal system. So and here we have, for example, a hexagonal mineral. Yeah, it's very nicely, and that is a quartz from the hot springs in Arkansas. So, and this external shape or the external form is caused by the internal symmetry. So, and now you can see these bubbles. Yeah, we are calling them always bubbles. And these bubbles are atoms. So and these atoms are always arranged in a certain order, yeah? So we have here red bubbles and we have here blue bubbles. So and what do you think when we have, here we have the mineral quartz. So and which elements you are expecting in a quartz? There's not too much inside. That is silica and oxygen, yeah? Because the chemical formula of a quartz is just SiO2. So, but now we have to decide, or not we, because I know it. But you have now to decide, and that we know which bubble is which element. So what do you think is the red bubble here? That is oxygen, yeah? So, and the silica is the blue bubble, because the silica is much smaller, yeah? So, and these are so-called Sticks models, yeah? So you can find in the internet different programs where you can run such simulations, yeah? So, but I'm using not a ball and stick model, I'm using always tetrahedrons and octahedrons. So in this quartz tetrahedron, because silica is always located in the tetrahedron inside, is always, silica is always tetrahedric coordinated, and such a tetrahedron looks like this. So, and now we need the oxygen bubbles. Then we are making it like here, we have here red. For the oxygen bubble, here we have an oxygen bubble, and here we have an oxygen bubble. And then we have in the back an oxygen bubble. Yeah, it can be in the back or it can be on the top. Yeah. So and just inside, we have then the silicon bubble. That is then here inside. So, but now if you are looking here at the formula, then it's SiO2. So in the SiO2, you know that Si is 4 plus, and then it's minus 2, and then it's balanced. Yeah, you know this game, or I don't know if Eleanor has done it with you or not. But it does not matter, I will do it now. So then you have then the silica is the quartz tetrahedron or silica tetrahedron is balanced, yeah? So then we have here the silica tetrahedron inside has here 4 plus, and then you have here O minus 2, O minus 2. And here also O minus 2. So then here 1 electron is left, 1 electron is left, and 1 electron is left. So how will you now solve this problem in the tetrahedron? You are just connecting the whole thing with another tetrahedron. So then you are putting here the next one, here the next one, here the next one, here, 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 there. So and then you have your silica again inside, and here you have your oxygen bubbles, and then 1 minus goes here and the other minus goes here, and here you are connecting the next tetrahedron, and there you can do the next one, and you can do this the whole day till the whole board is fully painted, yeah? So, and that is how these minerals are formed, yeah? So, and then you have different minerals having different crystallographic symmetries, yeah? So, and that is all controlled by the arrangement of the tetrahedrons and the octahedrons. So when this becomes then also deformed, because you have then in other minerals, you have then a lot of other elements inside. So in that we will also do now or later on in this class. Fine. So I don't know whether let's just keep them around. So then we can go to the next slide. So now we have another mineral, for example, that is a beryl. I don't know if we have a beryl or not. So in the beryl, that is has another silicate structure. For example, it's a ring silicate, yeah? Whereas the quartz is a technosilicate, yeah? We do this then also later today or next week. So, but anyway, that is a ring silicate, and such a ring silicate forms then always the coordination of rings. And that is then, for example, such a line. So then the next slide. Yes. So and now we have this different arrangement of the different atoms. So now I showed you some minerals where you have a very, very nice crystallographic symmetry, but other minerals which cool down faster when the melt cool down faster, or other minerals they are strongly deformed during metamorphism, or other minerals they did not have enough space to grow, yeah? Then you cannot see longer the crystallographic symmetry. Yeah? So, but now you found maybe, I mean, you are just walking around and then you are finding some minerals and then you would like to know what it is. So, and then you can, for example, just take an X-ray. So, in the X-ray, we'll show you then where the bubbles are located. So, and then you are getting such pictures, yeah, that for example, I mean, here you have a photographic slit, here you have the crystal, and then you are just running the beam through. So, and then you can find what you can see on your photographic slim or plate where the bubbles are sitting. So, that's, and that was actually discovered for the first time by the French physics Madame Curie. Curie with IE, yeah? So, that is Madame Curie, that is the French apostle. So, so don't mix it up with the curry, yeah? Something totally different. So, and she discovered this by an accident or coincidence. So, because she found some minerals, and I mean, she lived, I think, in the 17th or 18th century, something like this. So, and then she found some minerals. And some of these minerals, that was an uraninite or uranite. So and these are radioactive minerals. Yeah? So that means there you have a radioactive decay, and this radioactive decay, that is the uranium, the decay of uranium to lead. So, and there she saw it a few days later, because she put just this uranite on such a photographic sling or plate. So, and then she saw a few days later the shadows of the atoms or the bubbles, yeah? So what you are seeing here, that is not the bubble itself, these are the shadows. So the bubbles itself you cannot see. They are too small, but the shadows you can see, and I have seen them a couple of times. Unfortunately, I cannot show it to you because the next transmission electron microscope, I think that is in Sydney or in Melbourne, yeah. So, and they will not pay you the flight that I can show you the bubbles there or the shadow of the bubbles. I mean, it's actually very fancy, and if you have seen it one time, but maybe we can find a movie or something like this, yeah. We can maybe check it till Monday, then we can show them on the somewhere on YouTube. Yeah, there must be some around. So, and I have seen the shadows of gold bubbles under the magnification was 200,000 times. So, and then you can see them, these are just bubbles, yeah? So, when you can see them with such a microscope, you are just watching and watching and watching. So, and you can do this only in special rooms. So, there must be a huge or very thick concrete bottom. And you can also only do it during the night because of the traffic. So, for example, I mean, in this lab where I have seen them, that was in Germany, there was the main road there that was actually the same distance as from here to the Laukala Bay Road, yeah? So that is about maybe 200, 250 meters, something like this, yeah? That was there in Germany at roughly the same situation. So if there is traffic that means if a truck comes by, then you can see that they are starting then to steer, yeah? Therefore, you need, it should be, the best thing is during the night, yeah? So they are very sensitive, and of course, if it is, if you are heating up your gold, yeah, then you can smear that, then they just start to smear much faster, yeah? So that is the entropy and the enthalpy, which I will also introduce to you in this class. And that is actually very important, because that is very important for the mining industry or some other things like geothermal power and all this stuff, yeah? So, but it is actually very simple, and he will show you some experiments, and I will also explain to you where you can see or study all these behaviors of the bubbles in a daily life, yeah? Because everything what you are touching every day, everywhere, it's all bubbles. Yeah. So, but now you got this, you can use an X-ray beam crystal, a photographic plate or a slim here, and then you can see the shadows of the bubbles. So again, you can just calculate the arrangement where the bubbles are located, and then you know the crystal system, and then you can come, or then you can make some assumption or estimation. What for a mineral is this? It's actually an old method, and it's nowadays not very common, because nowadays you have just electron microprobes, then you are just making a scene section. You know what a scene section is? No, do you know what a scene section is? Then you just bring us some scene sections. Yes, here the Satan will just show you some scene section. So in that means we have a rock or something, a mineral or a rock. So again, we are just making such a very thin wafer, putting the wafer on a glass and grinding them down and cutting them down to a thickness for the electron microprobe of 80 microns. And for the best thing for microscopic work, that is 30 microns. So, and what is an electron microprobe? And with the electron microprobe, you can measure the mineral chemical composition, and if you have the mineral chemical composition, then you know what mineral is this, yeah? So, next slide. So now we have here a table which shows us or tells us something of the composition of the Earth's crust. So here we have in weight percent, we have 46.60 weight percent oxygen, then we have about 28, we have silica, we have some aluminium, iron, calcium, sodium, potassium, magnesium, and that is so the weight percentage of the continental crust as it is written here, yeah? So you have a lot of silica inside, but you have also sodium, potassium, and calcium. So, and less magnesium and less iron. Whereas in the oceanic crust, you have then less magnesium and less, you have much more magnesium, much more iron, but less potassium and less sodium. Therefore, you are forming in the oceanic crust different rocks compared to that or to those rocks which you can observe in the oceanic crust. Yep. So, and most of the rocks which we can find on this planet, these are silicates, yeah? So that means you have always silica inside most of the rocks, yeah? I mean, we have there also other rocks, but they are not that often, or they are not occur that often. That is the oxides, you know, like hematite or magnetite and all this stuff, or ilmenite. So then you have some carbonates, you know, like calcite or dolomite. So and then you have some sulfates and sulfides. And then you have also phosphates. So, and what is a very common phosphate which you are carrying every day around with you? I mean, I hope so that everybody is carrying them every day around with you. Here they are, these phosphates. If you are looking at an old grandma, you have no hope. So there you are carrying them around. That's your teeth in your mouth. Yeah, that's actually of the composition, the same composition like an apatite. Yeah, do we have an apatite? Yeah, let us check. So, but anyway, most of the minerals, these are silicates, and they are formed by the SiO4 tetrahedron, because on every corner you have the oxygen, which you can connect to another, with another tetrahedron, and inside you have your silica. So, yeah, if we can have the next slide, so it was stressing. So, and therefore we have then SiO4 polymers. We have there single silicates, we have double silicates, we have ring silicates. Can we just go here to the ring silicates? So, yes. We have here ring silicates, then we have chain silicates, and then we have double chain silicates, yeah? So now we can go just to the next thing, because I will repeat this all the time. For example, we have the mineral olivine. So in the mineral olivine, that is the most common mineral in the Earth's mantle. So that means 67% of all the minerals in the Earth's mantle, that is olivine. So, but olivine is not very common in the continental crust. Yeah? It's a mineral which you find mainly in the oceanic crust. So, when you had just today already an olivine in your hands, and I will just show it to you again. Here is the peridotite from the two peridotites. Yeah? The one from coral, this one, yeah, this one, yeah, if I can just have it. Yes, no, this is an underside. No, not this one, but this one, yeah. So this is now nersolite, and this very greenish mineral, yeah, greenish shiny mineral, that is the mineral olivine, yeah. So in this olivine is a single silicate, yeah. So that is it's formed here by single tetrahedrons, yeah. Here. So that means in the olivine the tetrahedrons are not connected directly with each other as I have shown it to you here, or if you have it when you are talking about parts, yeah? So that is the things, the stuff is not connected. So, but when you are looking here at the mineral chemical formula, then you have not only silica and not only oxygen, there is now here another guy sitting. And that is magnesium, and I just told you before, the oceanic crust is very enriched in magnesium, and then of course you are forming the magnesium-bearing minerals, yeah? So, and this is now a typical forsterite, yeah? Or every mineral, or not every mineral, but most minerals, they have different end members. So one of the end members of the forsterite, of the olivine, that is the forsterite, yeah? And that is the Mg2SiO4, and that is the forsterite, yeah? Mg2SiO4, that is the forsterite, and the shortcut is FO. Now we are making out of our forsterite a firelite, yeah? That is another end member. So, and what can you do now? Which element can you put in instead of the magnesium, which has, it has also 2 electrons in the outermost strip and is roughly of the same size as magnesium? Which mineral is, which element is this? It could be calcium, but then we would not make a firelite, then we would make a Hirschtenite. So which other element can it be? But you are right, it can be calcium. So do you have an idea? Just speak in the phone. I mean in the microphone, yeah. So that is the iron, yeah? That is the Fe2SiO4, yeah? So, and then we have replaced only the magnesium with iron. So, or we can have a mixture of both of it, which is actually always the case. Then you have magnesium and iron, SiO4, yeah? So that means the olivine consists mainly of the end members forsterite and firelite, but you are right, you can also put calcium inside, yeah? So, but the calcium variation is not that common, yeah? So, and now we have to think about where is this magnesium here, for example, sitting? That is here the blue and the yellow bubble. Yeah, that is the here sitting, that's everywhere, in this case magnesium. So, and why do you think the author has made here blue bubbles and here yellow bubbles? I mean the guy who has made this picture. So why is it here blue and here it's yellow? Yes. So because the whole thing is in always, every mineral is in three dimensions, yeah? So and these are just the different layers where the different bubbles are situated or located, yeah? I mean, it could also be that the guy who has made this picture was just drunk, yeah? So the next slide. So, and here we have now the quartz, which I have just given you around. So and there, it looks then different compared to the olivine before, yeah? Because the quartz has not single tetrahedrons, the quartz is a tectosilicate where all the tetrahedrons are linked with each other, yeah? So therefore, with all this different arrangement, the quartz has then a different shape and a different crystallographic symmetry compared to the olivine, yeah? So in here, yeah, you have again here the model as tetrahedrons, and here you have the ball and stick model. It's up to you which one you will use. There are just different things around, yeah. So, and one can see it from the back, yeah. So now we are just going to the next slide, please. So that means we have common silicate minerals, yeah. So that is the olivine, which I just showed you now, yeah. And I explained to you now the tetrahedron, independent tetrahedras joined by iron or magnesium. These are the two elements, or the two elements. So then we have the pyroxenes. The pyroxenes, these are single chain silicates. So that means, I showed you this before, the arrangement of the silica polymers, they are just forming single chains. So and therefore you have then also different end members. I will just show you. I mean, we have the group of the orthopyroxenes, for example, and we have the group of the splinopyroxenes, for example, yeah. So, and then we can subdivide them. We have here the end member N-statite, and here we have the ferrosilite. So, and now we are starting here again with this arrangement here. So all the pyroxenes on this planet, they have 6 oxygen, yeah? All of them, because otherwise they would not be pyroxenes. So then we have here the tetrahedral places, and here we have the N places. N1, no, the bigger one, that is the N1, and then the N2. On the tetrahedrons, as I told you before, we are making always the silica. So in the N-statite has the Mg. I mean, the formula is actually Mg2Si2O6. So the question for you is now why I'm writing it like this, because some minerals, they have very complex and huge mineral formulas, and then it is better to understand and balance them if you are just putting all the arrangement of the octahedrons and the tetrahedrons, and then you have just to fill it up. So then you are making here again iron. Yep. So and that is then the so-called Fm exchange, yeah? F for iron, M for magnesium. So in such an orthopyroxene is called orthopyroxene because it is orthorhombic. So now we need an orthorhombic crystal. That is this one. That is orthorhombic. So that is because here you have 2 magnesium inside, and here you have 2 iron inside, or you can mix them up. But they are always orthorhombic, and there you can see that the angles between all the axes, if you are just looking at this wooden model, is 90 degrees. So in the angles, that is alpha, beta, gamma, yeah? So, and now we have the clinopyroxene, and they are called clinopyroxene because they are monocline. So, and now we need to do the plots for that. That is, for example, this guy. So in there, the angles alpha, beta, gamma, they are not all of them 90 degrees. So now we have to think about, or you have to think about, because I know it, what happens there? Why has this mineral, is this mineral now orthorhombic, whereas the other one is monocline? I told you just before you have that the internal structures reflects then the appearance of such a crystal or mineral. So that is the arrangement of the atoms. So what can you do to disalign it in such a way that you have that you are making now a monocline crystal, whereas you had before right now an orthorhombic crystal. You are changing just the sizes from the bubbles. So and now it's your turn. What bubble has also 2 electrons and is bigger than magnesium and iron? That is calcium. You just mentioned it before. So then we have here, for example, the N-member dioxide, that is the shortcut is Di. Then you are putting here calcium, and here you are putting magnesium, Fe2O6, yeah? So why do you have a clue why I'm putting now here calcium and here magnesium? That is because the bigger octahedron spaces, we are putting that always in front, yeah? So when the calcium bubble is bigger than the magnesium bubble. So but now we are making an Fm exchange again, and then we are making an Heidenbergite, and then this calcium, iron, Si2O6. So, but now we are making a jadeite out of it, yeah? And I mean jadeite, or yeah, it's called jadi, or jade in German, yeah, because sometimes I'm forgetting the English explanation. So, and that is actually a gemstone, yeah? So you can carry around with it on your fingers or... So, but this jadeite has now here and on that side, on the N2 space, another atom. So, in which bubble is also big, and is actually very common. Not very common, but I mean it's not a trace element, yeah. Which bubble is this? That is the sodium. Yep. So then it's even bigger than calcium. So then you have here the sodium. So but now if you are looking at the periodic table, then you know the calcium has 2 electrons in the outermost ring and the sodium has only 1. Yeah, you know this. So has only one electron in the outermost rim. So, but if you are now just checking the dioxide or the Hedenberg ion or one of these guys, yeah, then you have here 2 plus, then we have 2 times 4, then we have here 8, and then we have 6. And then we have here, moment. Yes, we have the minus charged atoms, and then we have here 2 multiplied by 4, that is 8. So, and then we are adding this together, we are having 12, and then we have here minus 12, and then it is balanced, yeah? So, because if you cannot balance them, then they are just falling in part, yeah? So in the nature, this happens when we have alteration, yeah? When you have alteration, then you are removing some atoms, and then, for example, Vanuatu is somebody here from Vanuatu, Nambasa. No. Anyway, there you have the bauxite. Maybe you notice they are mining their bauxite, yeah? And bauxite, that is soil, yeah? So, and soil is a product of weathering. So, and this has then before it was a rock, and this rock becomes then weathered, and then it's falling in pieces, yeah? And then you have a soil, yeah? That's how you are creating soil, yeah? So, and now we are having here a sodium city. So, and if we would have here magnesium or iron, then our Chardonnay would just fall in pieces. So, what can we do now? So, we have here 1 plus. Then we have our 2 silica. And we have the 6 oxygen. It's always the same. So, but now we need here a bubble which has 3 electrons in the outermost rim, yeah? Otherwise you cannot balance it, yeah? So, and what other very common element has 3 electrons here in the outermost rim? Aluminium, yes, congratulations. That is aluminium. So, and now our Chardonnay is finished, yeah? That's the very simple how mineral chemistry works, yeah? It is just anorganic chemistry, yeah? So, but now we are making from our Chardonnay an agate. Shortcut is C. So we have here also a sodium. So, but now which element has also 3 electrons in the outermost rim and has nearly the same size of aluminium and is also very common. Which guy is this now? That is iron 3 plus. So these are then the most common pyroxenes. I mean, there are a lot of other pyroxenes around, but here in class I will give you only always the most important end members, that you have a little bit of playground. I mean, actually you can then also put inside, instead of the aluminium or the iron 3 plus, you can also put inside chromium. Yeah, chromium has also 3 electrons in the outermost rim, and then you have a pyroxene called the fuchsite. Yeah, but the fuchsite is not that common. Yeah. So then we have the amphiboles. The amphiboles are double chains of linked tetrahedrons. From these guys I will give you the next week all the exchanges because they are a little bit complicated. So and then we have the micas and the clays. These are 2D sheets of linked tetrahedrons. Do we have some amphiboles? Here we should have amphiboles. Amphiboles and micas. Then we have parts, yeah, you saw it just right now. And these are 3D frameworks of linked tetrahedrons. And then you have the feldspars. They are also 3D frameworks, but they have also aluminium, sodium, calcium or potassium, which can be substituted, yeah? So then if you are just going to the feldspars, if you have the feldspars, then we have the plagioclases. So and the plagioclases can be subdivided in albite and in anortite. And the albite is a sodium Al3 Si3O8. All the feldspars have always 8 oxygen. So but here we make our substitution between sodium and calcium. Then you know sodium is 1 plus, calcium is 2 plus. So that means we have to balance it. Then you are just putting one aluminium out. That is not an Al3. Then we have here 3 plus. So and then we have here 12 plus. And here we have minus 16, 12 plus 3 plus 1 is plus 16, minus 16 it's balanced. So now we have here a balanced albite. Putting here a calcium inside, then we are balancing it such a way Si2. So then we have here the minus 16, we have here plus 8. So when 2 multiplied by 3, that is plus 6. 2 plus 6 plus 8, 16, yeah, balanced. So and then we have the K-feldspars. That is this guy, that is the K-feldspar. And then we are putting instead of the sodium, we are putting the potassium bubble, yeah? Yeah, potassium has also one electron in the outermost ring. Then we can keep all the three silicas of 8 Al3 plus. So, and then we are painting or drawing just or writing just here. So, and this is then the K-feldspar. That's the way how it works. Yep, and to the amphiboles, most common amphiboles and micas, we are coming the next week together with the garnets. Yeah. So next slide. So these are the silicate minerals before, and I have just given you as a small mineral chemical introduction the exchanges. To get an idea, yeah. So now we have common non-silicate minerals. So and then we have the calcite, CaCO3, as a common carbonate, yeah. We have another carbonate that is the dolomite, yeah. Putting here apatite, magnesium inside. Then we have the apatite. That is the stuff what you are carrying always around with you. So then we have the halite, and halite, you know, you are using also everyday halite, or most of the time that is just salt, yeah? So that is the stuff which you are putting in your soup. So but then what else do we have here? We have gypsum. Gypsum is just a hydrated calcium sulfate, and we have fluoride. And fluoride, that is a calcium and fluorine mineral, and there we have a nice crystal as well. That is the fluoride, yeah. So and then we have here, for example, very, very nice biocides, yeah. So there you can see these booklets. These are all single sheets, yeah. So but can you see it here? Yeah, we will do this next week, while they are forming the single sheets, yeah. So but don't remove all the single sheets, because otherwise your friends next year will not have anything left. So here we have the apatite, how it looks in nature, yeah. It's a little bit greenish. There are maybe some other stuff inside. So and now we have the example here, maybe also highlight, yeah, just the highlight, I mean, we have just poured all this stuff really around. here we have a nice amphibole, yeah. So you can see here the symmetry, yeah. The amphibole is showing always up at 60 degree to 20, 24 to 56 degree. So we have a nice autoclass, you know, an autoclass that is then a K-feldspar. Here we have another mica that is a masquerade. So now we can just go to the next slide. So there we have now another quartz, and here you can see what I have told you now thousands of times today, that all the tetrahedrons are linked. Yep. Therefore, a quartz is a tectosilicate, yeah? So now we are going to the next. So, and here we have, for example, the feldspar, that is the albite, that is this guy, yeah? So, and then we have here the linked silica tetrahedrons, and here we have these bubbles. And these bubbles are then, is the sodium, yeah? So, and then you can replace these sodium bubbles by the calcium, but therefore, you have to remove a silica and add one aluminium inside. So, and therefore the anortite, which is this one here, is changing the symmetry, yeah? So, and therefore, the mineral chemistry of every mineral controls the internal mineral chemistry, controls the external symmetry. So, now we have here the feldspars, and I just showed you here the three feldspars. We have the albite, the anortite, and the K-feldspar. So in the K-feldspar, that is the autoclass here in this case, because K-feldspars can be subdivided in the microcline, the autoclass, and in the sanidine. They have all three that they have the same mineral chemical formula, but different symmetries. So when they are formed then at different temperatures. So and if a mineral has the same mineral chemical composition, but is showing a different symmetry, then these minerals are called polymorph minerals. So in the sanidine, that is the high temperature feldspar, and that is formed always, I mean of course at a higher temperature, therefore I'm telling you it's the high temperature feldspar, but the sanidine is occurs only in volcanic rocks, yeah? So in the volcanic rock, you know, these are explosivas, yeah? So whereas the autoclass occurs, I mean, if you are looking for magmatic rocks, it occurs then in plutonic rocks. So in the plutonic rocks, these are heterozygous. So if we are looking for metamorphic rocks, then the order class is actually the common feldspar. Yeah? So, or under amphibolite phasous condition, you will learn this later, what the amphibolite phasous conditions are. There you have then the microcline. So anyway, and there you have different subdivisions. I mean, here you have the pure albite, yeah? This one, at this corner, and here you have the pure anorthite on the other corner. So, and then you can have a mixture between all of them, yeah? So, because you can mix them up, yeah? So, and I mean, here you have then the oligo class and the andesine, the labradorite, the butonite, and here the anorthite. So, and here you have the sanidine, the sodium sanitine, and here the anortho class. And here you have an invisible region, and that means in this immiscibility region, no K-feldspar or plagioclase can be exist, you know, with such a mineral chemical composition. So, and that is now a temperature dependency. Because if you are at 800 degrees Celsius, you have here a miscibility gap. Yeah? So, and then such feldspars with this composition does also not exist. So that means such a feldspar with such a composition is then formed at higher temperatures. So, and therefore we are now at the next point. The most important parameters when we are talking about magmatic systems or metamorphic systems, these are controlled by the pressure and the temperature. Yeah? That is the most important thing. So an every mineral is formed at a certain pressure and a certain temperature. At every certain pressure and temperature, a mineral has a certain mineral chemical composition. Yeah? So, and then you can measure these minerals, and then you can calculate, or I can calculate, at which, hey man, how are you today? Yes, just wait, yeah. And then you are forming then certain minerals at a certain pressure and temperature, and after measuring the mineral chemical composition from all these exchanges, then I can calculate at which conditions they are formed, and therefore we can then reconstruct the Earth's history. Or we can find where we have, for example, ore deposit or something else. Yeah? So, and that was it now for today. So, and then I would just suggest we are seeing us then on Monday in the lab and Tuesday again in the class. Yeah? And you can meanwhile make a plan where you like to go to the field trip, yeah? Because we need a little bit time to organize it, yeah? Okay, the PDF and everything is uploaded on Moodle. The whole course material is uploaded there, yeah? Yes, Monday 5 to 6. Yeah. So for those who came later, we have now decided to have the class or the lab always on Monday between 5 and 6:30. So because otherwise some people have always clashes, yeah, and that is not good.
On Wednesday was on the timetable, but most of them This question, yes? And Tuesday too?
Okay, then we are making Monday between 5 and 6:30. No, between 5 and 6:30. And if you still like to change it, I mean, we are actually always available from every day between 5 and 6:30. Yeah. But I think Monday is okay, because then we have Monday lab, Tuesday class, and then we are done with ES303. Okay. And the movies then are always uploaded, but you can already start to watch the one from last year. Yeah, it's always the same.